welcome to the second day of ICML conference. People are still floating in. So let me introduce our second invited speaker, Aude Billard. Aude is a full professor. She's a full professor at EPFL and School of Engineering. Actually, she was a faculty at University of Southern California, so she's almost local. She received multiple awards, NSF Career Award from Swiss National Science Foundation, Outstanding Young Person from Swiss Chamber of Commerce, multiple Best Paper Awards. Her research spans the directions of machine learning and robotics, particularly when it comes down to working with sparse data and the need to do fast information retrieval. And her work also finds applications in robotics, human-computer interaction, human-robot interaction, and computational neuroscience. So without further ado, let us welcome Aude Billard and her talk on machine learning for robots to think fast. So thank you.
So thank you very much, Russ, for the introduction. Thank you very much to Kamalika also and Russ for accommodating me coming here one day late. And I want to apologize and thank also the previous speaker from yesterday because I was simply stuck at the border and I was waiting for a visa to enter the US. And so I'm really, really happy to be here. And I really thought I couldn't make it. And it's a pleasure to also be here at ICML. So what I'd like to talk about is how we can use machine learning in robotics and especially to help robots to think fast. And so all my talk will be between control theory, where we need control theory, what we are lacking in control theory, and where machine learning can bring something that we don't have in control theory. And with this, I'd like to start with a little bit of a teaser. So this is really what I have in mind by controlling super fast, is to have a robot which is capable of catching an object which is flying, as you can see it here. And it's flying only in a few milliseconds. So what is difficult there and what can control theory not do? Well, typically there is a huge amount of uncertainty. So if I just play the video once more, you will see that the bottle, as it's flying, is often rotating, and it's rotating on itself, and depending on how you throw it at the robot, then you will have a very different type of rotation. So there is no way that you can completely, fully predict the motion of the robot that needs to catch that. You will have to adapt on the fly, and there is a huge amount of uncertainty. And this is where machine learning can contribute to control theory, is to bring a way of modeling this uncertainty and to help the robot computing that. So to give you a little bit of an idea of how we do that, I will go step by step. And I will show you the different ways in which we can approach this from a robotic perspective. So I assume that a lot of people in the room are not familiar with robotics, so I will start with a very simple example. Assume that you want to catch just a ball. And so what you have to do is to compute a path to get to the ball and close your hand on the ball. Okay? And so assume that you have a path, then everything is solved. But the question is which path? In fact, there are an infinite number of paths that you can choose to go from A to B. And when you start from a different location A, you have another infinite number of paths. And so the question is which of those paths is optimal? And clearly, optimal control theory will allow you to compute an optimal path under a certain cost function and under a certain number of constraints. But when you want to catch an object in flight, you don't have the time to compute and do an optimization. Even if it's a convex optimization, even if you know that it's going to finish in finite time is not what you have on your hands. The ideal is to have what we call a closed-form solution. That means an analytical solution. And this is where machine learning comes hand in hand with control theory. We're going to find feasible paths from control theory, and then we're going to learn them and get a closed-form solution from machine learning. So the way that we approach this is to assume that we will have a functional, which I write here, and I hope that people can see my mouse. I don't know if this is visible. But so we have a functional, f of x, which computes a velocity flow. So we're going to control in velocity, and the drawing that you see here are, in fact, a path in velocity, which we see here illustrated in 2D, but when we control the robot, it's going to be at least three-dimensional, and then usually the velocity is also three-dimensional, or maybe seven-dimensional if you're controlling for the entire joint. So we have this flow of trajectory that brings us to the target. And this is given by this functional f of x. And assume that you have this functional f of x in closed form, then the advantage is that you don't have to do optimization. So Another thing that is really nice if we go with this representation is if target move, which is what we want to do, to catch something flying, then in fact all what you have to do is just to change the frame of reference, you place it on the target, and then actually your flow moves, and then naturally, because there is always a solution, then you move with the flow. So you don't have to recompute an optimal path, it's given by this functional f of x. Well, but that's where, again, machine learning comes into the picture. What is f? There are an infinite number of f that one could have. So one possibility is that you get demonstration. You get a human demonstrating here, as we see here. A human can drive the robot and show to the robot different demonstration, which I illustrate in blue on top here. An alternative that we also often do is that we will compute an optimal path, a feasible trajectory, a number of feasible trajectory from optimal control, which will give us demonstration, training data points. These are training data points, which are actually a representation of this function f of x, which we're looking for. Okay? And now we have to learn the function. But you're in machine learning, so you know how to learn a function like this. Okay? And you'd say, well, okay, let's apply any machine learning technique which can learn a nonlinear function. So I can apply support vector regression, for instance. And here is the solution when I do that. What we have here is a very good fit. We can see that there is a very good fit. You see the flow which is generated. There is some generalization around it. And it seems that it's doing perfectly well what we like to, but look at what happens close to the target. Close to the target, actually, when we reach a target, the pink trajectory represents the testing trajectory. So basically, I've trained my system, and now I'm testing it by starting from the initial location, which is the top trajectory. Same point, same as the training data point. I test it, I follow, it follows very accurately the path. And what happens when I get to the target? Well, usually what happens is that you have numerical, I mean, you know that you will have learned normally a velocity equals 0, but it's not exactly 0, and then you keep drifting. And the reason why you have that is that support vector regression, by construction, when you optimize for it, it does not know that it has to stop at the target. It's part of the data, but it's imprecise. If I train it with neural networks, any type of neural network, it's going to be the same problem. There is nothing that guarantees that I will stop there, and so I may be drifting. And that's, you can try this very easily with any MATLAB implementation. So what we need is actually to have a flow, and that's my desired flow, is to have something where I follow correctly the trajectory, so I've learned from the data, I have a good fit of my f of x, but I enforce that I stop. And that is where I will call control theory again back into the picture. What we know is that we want to stop at the target, and what we like at the target, which is called x star, is that actually our function is 0, so we want to enforce that it's 0. But more than that, we want to enforce that at the limit, all the flow, f of x, vanishes. So basically, it just says that it's a sink, and at this attractor point, all the flow vanishes. But I don't want to enforce that by generating lots of training data points all around the flow, spanning the space so that I will learn that. No, I like just to give a few examples, and then adding these constraints, making sure that the learn functional ensures these constraints. So how can I ensure that? One typical way of doing it is to do it with Lyapunov stability. So what Lyapunov stability says, and this is it's a shortcut, but just the gist of it, says that if you can find a functional v of x, so it's a potential, which is 0 at the point that you're interested in going, this fixed point, the attractor, and it's decreasing everywhere, then you're sure that you actually are stable and asymptotically stable at the attractor. But our problem is that we have neither f nor v. And this is, again, where machine learning can help. So if you're in control theory, by the way, you have to decide on an f or a v, and then you solve your problem. But here, what we like is to learn f and v. So how do we do that? Again, remember that what we have at our disposal at the minute are only data points. So we have training trajectory examples. So what we can do, one approach that we followed was to say, well, we're going to model that with a machine learning technique that we know of, which is doing a combination, a probabilistic model. So I will represent now the distribution of the data that I've seen, which is the distribution of position and velocity, okay, as a joint mixture of Gauss function. And what you see, if you're not familiar with this, the ellipse here, we have 4 of them for illustration. Each of them is an actual Gauss function, and the ellipse represents a isoline, a cut on the Gauss function. So we have, for each of those ellipses, the 2 ellipses, 1 standard deviation and 2 standard deviation on the same Gauss function. So we can learn this. This is a traditional technique in machine learning. There are many ways of doing that. You can do maximum likelihood. You can do variational analysis. And then the good thing is that what I'm interested in is to get this functional f of x. And this functional f of x, I can get it by taking the expectation over the conditional of my velocity given my state. What does that mean? That means that whenever I'm in a certain point in space, I can always condition to ask what should be the velocity at that point. And I can take the expectation for this. And the nice thing is that it gives you a closed form solution. This is what I wanted originally. I wanted to have a closed form solution. So by construction, Gaussian mixture regression here is a regression on a mixture of Gauss function, gives you a closed form solution, which is a linear combination of hk, which is simply the weight of the Gauss function. So it's a function between 0 and 1. And then it's a linear combination of ak times x plus b. Ak are matrices, which you need to learn, which you're learning. It's actually a combination of the cross-covariance matrices and covariance matrices of the Gauss function, and bk are vectors. So you can identify that. There are many techniques in machine learning to do that. But that doesn't solve no problem, because we're still going to drift. There is nothing that guarantees that we're not going to drift. In fact, what we can show is that if we choose a Lyapunov function, which is the simplest ever, it's a simple quadratic cost towards the target, then we can derive stability constraints for the parameter of this Gauss function. And basically, the first constraints that you see here, bk equal minus akx, is actually saying every single of these matrices needs to vanish at the attractor, so I need to enforce that it's 0. Okay, the function is 0. And then second to that, I can enforce the second Lyapunov constraint, which is that I need to decrease the flow as I'm coming close to the target. So underneath this drawing, what you see are the different Gauss and a Gauss function. And as you move towards the target, then the energy function, the Lyapunov function, is actually decreasing with this, and you can enforce that by constraints in AK. And so you end up with a constraint optimization problem, which you can solve by maximizing the likelihood or doing minimization least square, for instance, on the velocity and the position, under the stability constraint. It's a nonlinear, non-convex problem, but you can solve this offline. And the good thing is that in the end, you have this functional. You have this closed form solution with the guarantee. And this is what you will get in the 2D drawing, typically. You will get both highly accurate reproduction. You see in pink, it's a highly accurate reproduction, but it also stops, and you can see that there is a generalization around the attractor that enforces that the flow is actually really sinking on the attractor. And in case you're interested, we have here mldemo.epfl.ch is actually a software for different machine learning techniques that I use in the class that I teach, and you also have this this algorithm which you can play with. I said that we have neither f nor v. I gave myself a v and I solve for f, but I can also do it the other way around, because one problem when I choose a v like I did, which was a very simple quadratic cost, is that it's very conservative and it does not allow me to learn very nonlinear function. So I can instead say, well, I'm going to learn actually directly the v function, the Lyapunov function, from the demonstration. And it turns out that I can also learn that as a constraint optimization problem. And then what I can do is compute simply the gradient of v for getting f of x. Another alternative also that we've looked at in this paper is to train directly a so-called unstable dynamical system. So pick any of the machine learning technique that you like, support vector regression, neural networks, GPR, and then you can stabilize it in case it's not stable using similar type of techniques, learning a Lyapunov function and then constraining the final result. Now, what if you don't have demonstration? Well, if you don't have, starting training data point to start with, then one thing that we've looked at with a colleague, Jonas Büchli, who was at the ETH and now is at DeepMind, was to combine it with reinforcement learning. And so what we can do, and I'll be very brief here, is that we can, at each rollout, search for updates on this parameter of the function to ensure that stability constraints are satisfied. So it's also possible to combine this same principle of control theory into reinforcement learning. In this case, we had done it with pi-square. All right, so let me go back to my original problem. What I wanted to was to catch something in flight. At the minute, all what I've given to you is a way to get to a target when it's moving. And that's what you're seeing here. The target is the ball. The robot tracks it with its camera on board of the eyes of the robot. And it keeps moving the hands to track this and to stabilize once it gets onto the target. But this is only part of the problem, because if we want to catch the bottle that we've seen before, it's not a ball, it's not symmetric along 3 axes. So what we need is much more than that. And here is a nice illustration. If you want to catch this object as it falls, you better choose where you're catching it, and you better really adapt your grasp as you're doing it. So for instance, if a vase or a bottle I've shown before is falling, what happens often is that if you want to catch it at the neck, then you better go with a tight grip. That means a small hand. And if you want to catch it at the belly, let's say, then you're going to have a different grip. And if you don't choose correctly your grip, then what will happen is that if you go with a big grip and you want to catch it at the neck, it's going to fly through your hands because you haven't closed the hand on time. If you go with a tight grip and you want to catch it at the belly, then same thing. You're going to hit it, not close your hand because your hand is already closed and it's going to fly away. So you need to choose among these 2 different grips, and these 2 different grips are attractor. And so what we need is to have a multi-attractor system. For now, we've been able to learn one system from demonstration that gets to an attractor and has stability constraints, but we want more than that. So by now, you're familiar as to how we can learn one of these systems with a single attractor, but let's say that we have, for instance, 3 of them, 3 different attracting points. And for each of them, I have a function f1, f2, f3, and we can learn them separately. What we want is to learn a boundary between these systems such that if I start in a point very near to the boundary, slightly epsilon away from the boundary, then I should automatically decide to go to one of the attractor. And if I start slightly an epsilon away from the other side, then I should fall into the other attractor. And I want to do that in real time, and I want to do this with a single functional, which is again closed form. Why? Because I don't have the time to compute and do optimization on the fly. So let's do it one step at a time, and I'll give you just a bit of a gist of how to do that. Let's consider just a binary problem. I want to be able to switch between 2 different attracting systems. We went back to support vector machine, and we observed one thing with the support vector machine expression. So for those of you who are not familiar with this, then let me just quickly introduce that. Support vector machine does a binary classification problem. And so by construction, it decides that all the points on the left-hand side, for instance, of the boundary, will have a label which is called -1. And on the point of the right-hand side, have a label +1. And it takes a decision by taking the sign over a function, which I call here v of x. Traditionally in the literature, it's usually called h of x. Why do I call it v of x? Well, I'm sure you guessed it's because it's going to be my Lyapunov function. So the nice thing also with support vector machine by construction, when it learns this, is that at the boundary, this function is exactly 0. On the left-hand side, it keeps decreasing. It's negative and keeps decreasing away from the boundary. And on the right-hand side, it keeps increasing. So it keeps decreasing. That's awesome. So it is, by construction, a Lyapunov function. The only little problem is that by construction, it keeps decreasing, and it may vanish somewhere on the left-hand side of the boundary, but not necessarily what I want, which is not the attractor drawn on my illustration here. So how can I change that? Well, I can do the same thing as what I've presented before. I can go back to the optimization process, so go back to the equation of how do I optimize for support vector machine, and add new constraints. So for those of you who don't know support vector machine, you can just ignore that and wait for the video. For the other people who know this, you may recognize very quickly these typical expression for the optimization process. So in standard support vector machine, what you have is an objective function, which is a minimization of the norm of W, which is the margin, and plus some slack variable. Then you have a constraint, which is that all the points need to be correctly classified, and then you have a constraint from the KKT condition on the slack. But what we can do is we can augment this constraint optimization problem by adding other constraints. One of them, which is based on the actual Jacobian of the dynamics, to enforce that we follow the dynamics of our data points. That means that we don't just want the points to be classified as left or right-hand side of the boundary. We also want the velocity that is associated to the data point to matter. And we like that actually the flow follows the flow of the velocity at every single of these data points. And then we also want to enforce that we are stable at the attractor. That means that we stop at the attractor. We are 0. at this, which remember, that's the problem with support vector machine, is that it doesn't enforce that the 0 will be where we want, so we will enforce that. And the nice thing is that this time, we still preserve the convex optimization from support vector machine, so we can solve for this offline. And the other nice thing is that we end up, again, with a closed form solution. So let me just spend a little bit of time on this closed form solution. Again, for those of you not familiar with support vector regression, you just ignore the equation, but you just look at the drawing, and for others, you may appreciate the similarity with support vector machine. So support vector regression gives you a functional f of x, which is a linear combination of support vector, which we see here. Okay, that's easy to compute. It's fast at runtime. But if I do that, then, and I use only those, this is the drawing that you see here, I will have a flow which decreases away from the boundary, but does not stop where I'd like it. But when I solve with the constraint that I've added, what happens is that in the expression, the final expression of my support vector regression function, I have additional support vector, which we call beta support vector. These beta support vector, they come from the constraint that we wanted to follow the dynamics. So if we look at the drawing, what happens is that as I add these beta support vector, which are illustrated in this drawing as triangles, as I keep adding them, you see that the flow keeps moving with the actual dynamics. And then the last term, which appears here, is a bias term, which comes simply from the constraint that we requested that the flow vanishes at a particular point, which was the attractor. So it's a nonlinear bias, and it's enforced that the flow becomes 0 at the right point. So in both cases, basically, we can use machine learning. We use the way that these algorithms have been designed, and then we add constraint from constraint theory, such that we get the nice property of machine learning, learning a very nonlinear dynamical system, for instance, here, and at the same time preserving stability guarantee. And then, for instance, if we have learned 2 of those functions, then we can at runtime compute the f of x by simply taking the argmax over the difference. So here is a video of implementation of this. Here, what we will try to do is to catch this bottle. So same thing as what I've described before. You can catch it either at the neck, so with a tight grip, or at the belly. And you have 0.2 seconds to make a decision. And simply we switch across these 2 different attractors. And so you see that we're actually tracking the bottle from the camera, which are on board of the ceiling, very fast at 250 hertz. And there are really very, very little time, and you really have to make a decision in real time, because otherwise it's just going to fly from your hand. So if you slow down, then you can see that it really has to act fast. And when you see it close from the robot, it's easier to really appreciate that you really have no time to make a decision. Moving on one step further, again, I want to catch a bottle, or I want to catch an object. And if I want to catch an object such as this one, for instance, which is a racket, tennis racket, then the further difficulty is that where I want to catch it is not at the center of mass. So basically, the object flies like this. And if I'm a little nasty, as in the first video that I've shown you, where I really make the object spin, then what happens is that I have to predict the spinning. In the earlier video that I've shown you, the only thing that we were doing was to drop the object down. So when you drop it, then it doesn't spin much. Maybe it rotates just a little bit. But if I really throw it at you and I make it rotate with arbitrary rotation, it is very difficult, because it's definitely not a ballistic motion. And so it keeps spinning, coming back and forth. So this is, again, where machine learning is quite useful, because what you can do first is simply to throw objects and observe them. And as you do that, you observe them with camera, and so you get a lot of training data points. And then what you can do is learn, in fact, a representation of these dynamics. But you cannot do that with an explicit model, because it's fairly difficult. What is the description mathematically of the racket? You need to have the moment of inertia. You need to have the air drag on the racket, which will very much depend on the actual friction coefficient, etc. What we know, on the other hand, is that Newton, the law of Newton, still holds. So certainly there is a relationship between the acceleration, translational and rotational acceleration, and the velocity and the position. So what we did was to, for instance, train support vector regression. We actually compared with many different techniques. SVR was the winner in terms of both the accuracy but also the speed at retrieval time, at testing time, which matter for us. So we can simply say, and that's what you see as the equation there, is to say, well, I'm looking now for learning to predict, I want to predict the acceleration the translation acceleration and the rotational acceleration, given a set of kernel applied on both position and velocity. And once I've done that, then again, I can exploit the fact that support vector regression gives me a closed form solution, and so I can derive it and plug that into extended Kalman filter to account for the noise which is inherent to my sensing system. So again, a win-win situation between traditional extended Kalman filter control approach and machine learning, which allows you to really represent very complex nonlinear flow. So what do we have now? We have almost everything. We know how to adapt to something that moves and how to get there in real time. We know how to predict the flying trajectory of an object. But the reality will hit us. And the reality is that as the object flies, that's what you estimate, what you measure is often different. And if you suddenly measure that your object is not where you thought it will be, then you better adapt. And you have to recompute now a path, so predict our head of arm, and then compute where to get to the object. So all of that we can do. We have the technique for that. But what we don't have yet is the grasping point, is where I will intercept the object. And I need to choose this intercepting point smartly, because reality is super noisy. So I want to give myself the maximum chance, and this is again where we can leverage from machine learning. What does it mean to give myself maximum chance? I need to choose a region in my workspace as a robot where I have most chance to not drop the object. And so one possibility to do that is to represent the workspace of the robot by sampling it. So we can sample that and get the probability distribution of the configuration that the robot could have. And the reason why we need to do that is that at runtime, the robot will have to adapt its orientation to the object flying. And if there is a slight change in orientation as you're measuring it, then you need to be able to really quickly change your orientation. So you cannot be at the end of your workspace where you're completely stuck and you have no room to move anymore, because the robot has the same problem as a human arm, is that there are regions where you simply are non-convex and you cannot move anymore. So he needs to find a region where he has most possibility to arrange its wrist and change the orientation and potentially change a little bit the position to adapt. So we can represent this by simply learning a probability distribution function over the distribution of position and orientation. And the region which is the most likely to not yield failure is the one which is the denser, the densest, so we can just use the likelihood. And at runtime, we can do a line search on the likelihood of the region that is traveled by the object and choose the point which is the most likely in terms of the configuration space. Okay. So and this is the few result. So this is you can appreciate that indeed there is a real need to adapt in real time the orientation and the position as the object is flying, and you have really to do that as you observe the object flying. You need to also start moving as soon as the object is thrown at you, because there is no time to decide as it's coming closer. I like this video because it was a bit of a surprise for us, but it also shows the importance to be able to adapt in real time and to exploit this redundancy of configuration. So let me just play it again. So there is a bit of a mix between the adaptation and also just the hardware rotating at the same time. But I thought that was pretty nice. And also, this is probably my favorite, is to be able to catch a bottle which is half filled with water, whatever is the content, because this clearly you cannot represent with classical control. How can you represent the water flying in the bottle as it rotates? So that's where really machine learning is useful. And of course, to do that, we learn the model of the bottle by throwing it a little bit before. We extended that 2 years ago to enable 2 robotic arms to catch also objects in synchronization. I will not talk too much about it because there we really need to have control theory to ensure that the 2 robotic arms move synchronously and stop and get to the target at the same time. So this is just a video for you to appreciate the importance to really be able to compute at runtime. You can see that the 2 robots will really change completely trajectory depending on how the object is flying. And so one may go up and the other one go down, or conversely, and it's impossible to know that in advance. And they need to get to the object simultaneously. So this is not machine learning. This is more control and how we can ensure this synchronization between the 2 arms. But of course, we leverage from this ability to have closed form solution learn from the trajectory. I'm showing that to you because I'd like to introduce one other aspect where we use machine learning to help control of multi-arm system. And this aspect was in a problem of computing collision-free paths. So as soon as you start having many different robots, and especially two robotic arms, what happens is that they share the same workspace, which I illustrate here. So there are high chances that they may collide with one another because they're sharing the same workspace. So you say, well, okay, one simple solution, just put them apart so that they don't share the same workspace. Well, yeah, but if you do that, then there are often reasons for not doing that, because then you lose a lot of the space that you could be using for both arms. And also, if you think of all the humanoid robots that we have, humanoids means that they look like a human, then they have the two arms very close to one another, like my two arms, and they do share the workspace. And it makes sense, because you want to pass objects from one another, and you want to hold objects. But you don't want them to prevent from entering the other robot's workspace. You want them to exploit this entire workspace and ensure at runtime that there is no collision. So how can we ensure that? So one possibility is simply to build a map of this feasible workspace and then sample from that. So we can sample all possible configuration offline because we have the kinematic of the robot, so we can do that in simulation. We can move the robot and compute all the points that lead to a collision, all the points that lead to no collision. It's a real machine learning problem. And this is a representation of this machine learning problem, of course, in 2 dimensions. We are 14-dimensional because each of the robots has 7 degrees of freedom each. So in this representation, what I have in green are the non-collided joint configuration. It's a highly non-convex space. And in red, I have the collided joint configuration. Think of this as the joint space of the two robots. And they collide only when jointly they are in the same location together. So I can learn that, and I can do, here I apply support vector regression, and I can get, again, something which I really like, which is an explicit function of where I am in that space. So with support vector regression, I will learn a function gamma of what I call Qij, which is this joint space between Qi, the robot I, and Qj, the robot j. So it's this 14-dimensional space. I can train support vector regression such that outside, in the collided region in red, it's negative, decreasing. At the boundary, it's exactly 1. I can change that with changing the bias. And inside, it's positive. And why do I do that? Because I want a gradient again. And why do I want a gradient? Because this gradient will allow me to move away from the boundary. And I'm not going to go into the detail, but there you can then solve this at runtime. You can formulate it as a quadratic problem, and then you can solve this using the explicit boundary that you have. So I don't want to talk about the control problem, but I want to talk about the machine learning problem. Because for us in robotics, it's rare that we end up with millions of data points. For you, it's usual. But for us, it's a little bit less usual. So we ended up here with a lot of data points. We had a lot of data points for the collision, close to 3 million for the collision, 3 million for the non-collision. And so what happens is that even if support vector regression is cheap in the end and gets only 10% of this data point for retrieval, it's still very costly. And we wanted to be able to compute that at the runtime, at the closed loop control of the robot, which is 2 milliseconds. So this is what I illustrate this. This is a little bit the budget that we have in terms of computational time. And that means that we can have no more than 4,000 support vector. But 4,000 support vector was not accurate enough. So we had to find a variant on sparse support vector machine to sparsify that and bring us down to 98% accuracy with less than 2K. 2,000 support vector. And once we have that, then we can do what we see here. So these two robots are actually tracking the hand of Sina here, Sina Merazavi, who was the first author on the paper, and tracking the two hands. At the same time, they're continuously computing the configuration that will lead to a collision. So there is a adaptation, tracking, similarly to what I described before with a dynamical system, tracking for the hands for each of the targets separately, and then enforcing that they will not collide with one another and accurately follow the two hands motion. Just to close and to go a little faster and in less detail, I'd like to talk about other machine learning applications for robotics that we do in the lab, which have more to do with fine manipulation. So I'll be fairly brief here and just give you some highlight of what we're interested in doing. One thing that we've done for quite some time was to look at how we can get a robot to grasp objects with a grasp that really resembles what humans do. And actually, humans very rarely grab the object by just the main part of the object. Sometimes we grab it from the top or from the bottom, whether we want to hand it over or whether we want to keep the lid on. There are many reasons. So what we could do was, in simulation, using optimal control, compute for all possible grasp for a given cylinder. And then we will end up with lots of them. We had 2,000 possible grasps. And then we could use machine learning to cluster that and to recognize that there were certain categories of grasp that were always the same. And the nice thing is that when you had clustered these typical grasps, which are called pre-shape, then you could end up being able to grasp many different objects, as we see here, with the same typical grasp. And we can also find these grasps at runtime using representation of Gaussian mixture model. So these are just implementation of the robot grasping these different objects. And as you can see, there are different configurations of the finger that can be placed on the object. And I strongly believe that this is important to really enable robot to start manipulating objects similarly as we do in coordination, potentially also with others. Other thing that we've done was to enable robots to learn the feasible space and to embed that in, again, a representation from machine learning, which resembles a lot what I've described for the configuration space. So what we are doing here is teaching a robot using the compliance and the fact that you can move the fingers to show to this robot the extent to which it's OK to hold this object. You can move it around, and you're not dropping it. And once the robot has learned this configuration space, which lives in tactile space as well as in joint space, then you can push the object, and the robot will adapt the finger, and it will adapt the motion under the perturbation. You can also use similar model and extend that to have the robot, for instance, adapt naturally when you put more weight in the object, as we see here, just increasing the stiffness, so increasing the pressure. So we can learn how much pressure should be applied in different circumstances. And then we can also, and that's the video on the right-hand side, which is really nice, is that at runtime we can also have the robot sample and decide where to place again the finger and change the finger to restabilize the object as it moves. So if you push around an object, as we see here, the only way that you can stabilize it is by having the finger move and potentially also replace themselves on the object to restabilize, basically to cancel, in fact, the interaction forces. So there are ways in control theory where you can compute that and you can solve a constraint optimization problem, but again, this is slow. And the advantage of learning that is that you have a manifold of feasible space which you can query at runtime. The last thing that I just wanted to mention is the fact that we badly need machine learning when it comes to actually manipulate what I call deformable object that deforms as a function of manipulating them. And this is a nice example. If you scoop a melon, which I'm sure you may get the chance to do here because there are really very nice melon around, the problem is not so much how to scoop and move the arms and so forth, is to model the melon. And if anybody can give me a theoretical model of the melon, I'll buy that, but I don't think it exists. And to quote Danica Kragig, who once said, it's one thing to have a model of the melon from a computer vision point of view, it's another thing to actually have a model of the chopped melon and the pieces once they are chopped, because that can be anything which is orange and looks like anything that is orange. So this is where it's useful to learn, and I will not go into too much detail, but what we've done was to teach robots by, on the one hand, holding the robot arm and then also putting lots of sensors. We have here sensors on the finger of the person. We have sensors that measure the displacement of the grasp. We have force torque sensing that measure the force both on the melon and on the tool. And what we are learning is actually how to adapt what we call the impedance. So when you start scooping a melon, there are no two melons that are the same. Some are softer, some are harder. Actually, as you scoop, the texture changes also because they may start becoming more watery. And so naturally what you do is that you adapt this as a function of sensing the changes in the resistance, the force. And so we can embed that, and we can learn, in fact, this change so that we can retrieve it at runtime. And to convince that we could do that, naturally, what we have here is a repetition of the same task. And we had lots of melons for 2 months, I can tell you, because we had to each time change the melon to prove that it would work for many different melons. And the nice thing of learning that from a human and robot perspective is that you can have either the system being done, and I'll replay that, from the robot's perspective. So let me just go back. So we can have the human being a master, the human being the slave, basically the robot is scooping or the human is scooping, or we can have 2 robots scooping. And so learning this interaction force allows you to change the role naturally. We also recently extended that for other type of tasks, such as grading a zucchini. There again, I mean, no 2 vegetables are the same, so one difficulty here is to adapt to the shape of the zucchini, to adapt the force so that you don't break the zucchini, and to also be able to decide when you need to start to continue peeling. So you cannot just embed that as a sequence of tasks where you do it 1, 2, 3 times, because then you will start peeling too much. So this is where we used also, we developed an automatic segmentation algorithm, and we could also detect from vision when the zucchini is not sufficiently peeled to call for new peeling motion. And this is the reproduction where the 2 robots will go there. They have this multi-attractor system. This is a variant on what you've seen for catching object in flight. This time they will go to the same place, the zucchini. They will start peeling. And then they will use this automatic recognition of whether the zucchini is well peeled or not to decide where to go and how to peel it again. And also to change simply the length of the peeling, so basically the attractor, based on how long the zucchini is, all of that in an automated manner. So with this, I want to close. And I'll just close with a few words. So to me, it's very, very important that the community, the 2 community in control theory and in machine learning work together for robotics, because we have to talk with one another, and there is lots that can be gained. Control theory gives you a lot of guarantees. It gives you a lot of information as to how to describe the task. But we need machine learning to really embed this model of uncertainty for very complex things, especially for things that are difficult to model explicitly, such as catching objects that are half filled with water or manipulating deformable objects. This is the website of my lab. There we have source code for every single of the algorithm that I've shown. We also have run a few tutorials, the publication and also the video. And I really want to thank, of course, all the funding agencies that have supported this work, and in particular the people. And I want to thank Mohammed Kanzari, who was the very first one who developed the learning system that I've presented at the very beginning, so the asymptotic stability of the attractor. Ashwini, who did all the multi-attractor system. Sung-Soo, who was the master behind all the catching in flight object. Sina and Nadia, who did this bimanual catching, and Nadia has also done a lot of this manipulation of soft objects, which I've shown before. And of course, the team doing the robust manipulation and the people working on deformable objects. I thank you very much for your attention, and I'll welcome questions.
So if you have any questions, come to the mics over here. And
here. Hi. Thank you very much for the great talk, impressive results. I'm a physicist, and I wonder, because you need to learn the Newtonian dynamics of a given object, what is your experience and thoughts about generalizing to other objects, different kinds, and even like different masses of the same kind of object? Do you have any thoughts on that?
So two answers to that. The first, if I may just go back, actually in this work, which I just very briefly mentioned, here we're actually generalizing. So what we are learning are different grasps, and they generalize across many different objects. What we found is that, in fact, it was enough to have about 10, 15 different clusters, different grasp, pre-shape, and then you could grasp many different objects with this. It's more difficult to say which object we should grasp, which we haven't done. And it could be interesting to actually learn the category of object and to be able to associate what are the properties of certain objects which allows me to choose each of these grasps. I think there are a few people who have done that, in fact, on robotics. That could be interesting. But there is definitely generalization on that. For the deformable object, we haven't tried yet. It's certainly, I mean, the same algorithm, if you want, for scooping the melon, we can use the same algorithm for different type of force interaction that requires. In fact, the zucchini and the melon was quite similar in terms of the algorithm. But in the end, it was not the same model. So each time we could use the same algorithm for learning it, but it wasn't the same model. So I like your question. I think it's really what is missing, and actually it's on my to-do list quite high, is to really be able to now use and build upon the different model that we've learned and not each time learn a new one. Yes.
Thank you.
Thank you.
Hi, hello.
Hi, Raya.
Hi. Thank you for the lovely talk. Really nice. I'm thinking about the use of simulation, and with robots like the KUKA arms, of course, we have the kinematics are very clear, and we have a lot of precision, accuracy in simulation and with the real robot. But I'm wondering how you would handle a problem like the bimanual collision avoidance if you didn't have those models, or if the robots were not as accurate, if you just needed to handle avoiding bimanual collisions directly on the real robots.
Yeah, thank you for the question. So one possibility would be, and this is something that I haven't shown, but we do a lot of work on compliant control such that they're soft. So what one could do is to have the robot sample their space in a safe manner, a little bit like a human learning about its own body. So moving around and then touching each other, but of course they should really move very softly, and as soon as they make a contact, they can detect that. Actually, the KUKA has force torque sensing at every single joint, so you could measure that relatively precisely, or we can do that with camera, and then one could use this. It would be much more time consuming to get that, that's clear, but it would be totally feasible. One will just have to make sure to not break the robot by doing so. But I think this is totally feasible.
Like a baby learning in a padded environment.
I'm sorry?
Like a baby learning in a padded environment, right?
Yeah.
Some safety there.
That's true. Yeah, we could maybe pad the robot. Actually, we have covered the robot with tactile sensors, some of them, and so we could also use this tactile sensing for measuring explicitly. In this, the robot that you see here, the iCub, is actually the brown cover that we see on the slide. Is actually, these are tactile sensors, so it's actually covered with tactile sensor everywhere. So this robot could actually really touch itself and learn its own configuration space from this. Yes.
Thank you.
Thanks.
Hi, I was wondering how sensitive is your approach to the choice of kernel when you do support vector regression?
All right, so polynomial kernel cannot do the job, full stop. For many reasons, we can discuss this offline, but just theoretically speaking, it's very limited. So RBF can of course do the job because you put lots of different RBF functions, and the problem was simply to find the right value for the kernel widths and things like that. So what we did was to do traditionally a grid search on all the possible values of those, and we chose the algorithm that was the least sensitive to the choice of this hyperparameter. And the reason for that is that we really wanted to make sure that it was not by chance. So basically, we, in the paper, if you check it, you'll see that we had a map where we really looked at the prediction across the different parameters and changing the C factor, for instance, changing the kernel width, and making sure that we had a broad range of values of C and the kernel width, which will still lead to the same performance, so that it shows that we had real generalization and not just luck with certain parameter.
Hi, I have a question. In your opinion, what is a major challenge for the future research in this direction?
I'm sorry,
What is the major future challenge for this research?
So to me, really well, two of them. I mean, the major challenge is really to manipulate objects as we do as humans. Objects change just as a result of the manipulation. In fact, the very concept of object is a bit particular, because if you look at all the cooking tasks, we get object at the beginning and then we get another object from mixing them and changing that. And how to represent that, how to adapt to that, how to generalize and not have to relearn a new model, this to me is the real hurdle for robotics if we want robotics to really be useful in manipulation next. So this is maybe my priority currently.
Thank you.
Hi, good talk, thank you. I just wonder how your work will apply to the object that change the dynamic over the environment. For example, if you want to catch the ball that's running over the surface that's uneven.
So if you wanted to catch a ball and let's say like a snowball, and as it rolls, then it loses snow and then it changes its dynamics, that's your question? That's fun. If you've never seen it before, what will happen, well, one thing is that if it only slows down naturally because of the dynamical system, as it slows down, the dynamical system will slow down too, because time is implicit, and we're time invariant. So if the thing speed up, then I speed up because I want to catch it. If it slows down, then I will slow down. So that's not too much of a problem. I guess it's only if the dynamics will suddenly change drastically, but if the motion is slow enough and I have time to adapt, that's a little bit like the ball that was moving. When it's slow enough, in fact, I don't even need the prediction ahead of time of the flying dynamics, because I can just adapt slowly and catch it. If, in fact, my motor are faster than the speed at which the object is moving, then I will be able to adapt. That's not an issue. The issue is if your ball was coming down real fast and then losing a lot of snow, and then at the same time maybe changing into something else, which is a snowman, and then starting to move in a very unpredictable manner, then for sure, if I've never seen that, I may start running this way and then it will just pass me. So there, clearly, it will be as clueless as us if we have to face something we've never seen before. So that would be the limitation. Now, the good thing is that I will hope that if the robot has recorded that, then it could learn and do better. And with that, I'd like to maybe point out that, to me, this is also the strength between control and machine learning. Control is there to help you find a solution to something you've never seen before, but for which you have enough information, and then you solve for feasible paths. But you don't want to do that all the time. Once you've done that, then you want to learn it. It's a little bit like you coming to this room. The first time you were looking for the room, you search for it, but then the next day you know where it is, and then you just go straight. So again, if you've never seen it, it will probably fail. But once you've seen it, then it could update the model. One thing that I haven't shown also is that one can update the model. So we've done a lot of work where you have a dynamical system, which is learn, and then you can update that from this one to either add obstacles or change the compliance of the system, or simply change the trajectory as with reinforcement learning.
Thank you.
Hi. You demonstrated really nicely how difficult is the task of, for example, grasping a flying bottle or something like that. But at the same time, we're already starting to see self-driving cars. So is driving a car so much easier than catching a bottle, or how do you explain that?
So I don't know if driving a car is really so much easier. It depends. If you drive straight, or if the path is free, then yes, it's a 2D problem, and it's a navigation problem, which is to some extent easy. But if you had to drive a car and predict lots of pedestrians walking in random manner, which would be a little bit like avoiding the flying object, then I don't think it's that a trivial problem. And I may politely disagree that it's a solved problem. Yeah.
Okay, well, let's thank our speaker again.
Okay, so next we have our Test of Time Award. The Test of Time Award this year is given to Online Dictionary Learning for Sparse Coding from ICML 2009, and the authors are Julien Mayral, Francis Bach, Jean Fons, and Guillermo Sapiro. So let's give them a big hand. Congratulations. Congratulations. And these are your certificates.
Thank you.
This is for you. And we have 2 extra for
We
you.
are carrying that. Yeah. Yes.
Wonderful.
Congratulations.
Thank you.
Congratulations.
Thank you.
Congratulations.
Let's see if it's. I think it's all good.
So thank you very much to the committee for the honor. In particular, when we wrote this paper, Julien and Francis were just starting their careers. So it's a great honor to reward young investigators. So Julien is going to give the talk. Thanks again. Have a great rest of the conference and a great Pride Month. Thank you.
Well, thank you very much for this very kind introduction. I would like also to thank the Committee Award for choosing this work, which is about an old ICML paper, which was in fact also followed by a long version which was published at JMLR, and it was called Online Learning for Matrix Factorization and Sparse Coding. And so this was a joint work with Francis Bach, Jean Pons, and Guillermo Sapiro. Turns out you have seen Guillermo already, but unfortunately Francis and Jean could not be here. So here the only thing I can do is to show them their pictures. So now, what are these papers about? So they are dealing with matrix factorization. We have data points that come as the columns of this data matrix X, and we would like to explain X as the product of 2 matrices, D and A, where D has a limited number of columns, and we're going to call D the dictionary. Now, we are in fact interested in cases where we have some a priori knowledge about D and A. In particular, we like the case where A is a sparse matrix, and we call that the sparse coding problem. But in fact, there are also other situations that you may want to address. For example, you may want to look for a sparse dictionary D, but A is not sparse. Or maybe you may want to have both factors that are sparse. Or even sometimes the sparsity is not enough, and you would like, in addition to that, to also have a particular structure. For example, here you will see that in this dictionary D, there is some sparsity, but there are also some variables that are grouped together. Sometimes as well, you may look for a specific structure in the dictionary which is not sparse. As an example here, the columns of D, which are the dictionary elements, are representing piecewise constant signals. Now, what is now specific to this work is that we are considering problems where the data matrices have many columns, or even an infinite number of columns, but even in this setting, we would like to find a good dictionary D such that there is a factorization. So in terms of formulation, X is our data matrix. The columns are the data points. D is the dictionary, and the columns of D are the dictionary elements. And the matrix A carries the decomposition coefficients of X onto D in the following sense. If X is close to a product D times A, it also means that every data point Xi is close to a product D times alpha I. And if it turns out that alpha I is a sparse vector, it would mean that every point Xi would be close to a linear combination of a few dictionary elements only. So now here is the formulation we want to address. What we want is to find a dictionary D that satisfies a set of constraints. And we want the dictionary to provide a good representation for every data point Xi. So what does it mean to provide a good representation? It means that given X and D, we want that there exists a vector alpha such that X is close to this D times alpha. We want also alpha to satisfy some constraints. And there may also be a regularization function psi that would encourage a particular structure. For example, if you are looking for sparse solutions, you may use a sparsity-inducing function here. Now, I said we are interested in cases where n is large. So what happens when n goes to infinity? In fact, we obtain the problem that we really want to solve, which is a stochastic optimization problem, where x is drawn according to the data distribution. So here, this formulation is in fact fairly generic. But what is interesting is that if you start playing with various sets of constraints for D and A and with various regularization functions, you are going to recover many existing formulations. For example, if you want D and A to be non-negative, what you obtain is a stochastic variant of non-negative matrix factorization. If you now simply ask the dictionary elements to have bounded norm, and if you use also a sparsity-inducing regularization function for psi, then you get the sparse coding formulation. So as an example of function that induces sparsity, the L1 norm is very known for that, in the sense that if you are using the L1 norm for psi, then it will encourage sparse vectors alpha. Now you can also play with all of this. For example, you may combine sparse coding and non-negativity, and you get what is called non-negative sparse coding. If in addition to sparsity, you add another regularization function that will encourage a particular structure, let's call this function omega, then you get something that we may call structured sparse coding. And also, if you start regularizing the dictionary, for example, you may use the L1 norm to design a constraint set for your dictionary that will encourage here sparse dictionaries, then you get something which is relatively close to what is known as sparse PCA. And there are, of course, plenty of other variants of all of this, and I don't want to go into all of them. So now I will focus on the sparse coding context, okay, which is one of the simplest formulations I presented here. So this formulation was introduced by Olshausen and Field in '96. And it's interesting, it raised the attention of the scientific community because it was the first time, I should say together with independent component analysis, that a very simple unsupervised learning principle would lead automatically to various sorts of, let's call them Gabor filters, when trained on natural image patches. So the image on the right that you see does not represent the filters of the convolutional neural networks. What they represent is a set of dictionary elements that have been trained using sparse coding. So that means that these small elements are simply the columns of our matrix D, and the natural image patches will be the columns of the data matrix X here. So remember that we can play also with various sparsity-inducing penalties that also add some structure. So as an example, this is what happens if you start adding some hierarchical structure in the dictionary elements or topographic structure. And for those of you who are familiar with independent component analysis, you may recognize something that looks like something called topographic ICA. So now sparse coding in the context of, meaning sparsity in the context of matrix factorization was introduced in '96, but in fact the sparsity principle, which consists of explaining data or observations with as few variables as possible, was introduced much earlier than that. So I believe that the first time this principle appears for statistical modeling is in this famous paper by Wrinch and Jeffreys in the 20s. So this is a paper that introduces a simplicity criterion for science to perform model selection. And sparsity, meaning the number of parameters of a model, is one of these aspects of simplicity. So then later, sparsity was used in many times in various contexts. It was used, for example, by Markowitz in the 50s. There is a very large body of work in statistics about what is called best subset selection in the 60s and 70s. We may call the 90s the wavelet error in signal processing. And then we have the lasso estimator in statistics, basis pursuit in signal processing. In 2004, we have compressed sensing, which has had a huge impact. And very important for us, we have Elad and Aharon's image denoising method in 2006, which achieved state-of-the-art results at that time. And so that's really what triggered the interest of the image processing community for dictionary learning. So here is now the context of 2009, 10 years ago. So at that time, we had already many successful stories of dictionary learning, essentially in image processing and signal processing. So we had stories about image denoising, in-painting, demosaicing, super resolution. For example, this is what we were able to achieve 10 years ago. We have an image on the left which has some text. You want to remove it. And if you use sparse coding as a tool to model the local appearance of natural image patches, we are able to recover the image on the right. And it's very hard to see that this image was corrupted before. There were also successful stories in computer vision for modeling local features. So in 2009, dictionary learning on top of SIFT wins the Pascal VOC09 challenge by Yang et al. There is also another variant that wins the ImageNet 2010 challenge by Lin et al. And you know what happens when a technique wins the ImageNet challenge, then it gains lots of attention. So more generally, matrix factorization is also becoming a key technique for unsupervised data modeling. It was used to win the $1 million Netflix prize, which is the ancestor of Kaggle. It's used for document clustering, for genomic pattern discovery, and for plenty of other applications. So still in 2009, so there is a classical approach to perform matrix factorization, which is alternate minimization. So here is a formulation for matrix factorization. It turns out that if you fix one of the two factors, D and A, and you optimize with respect to the other one, very often optimization becomes easy. So then it's very natural to alternate between the minimization of D and A and hope to get a good solution. So it's very practical, very simple, but the only drawback is that it requires loading all data at every iteration. So it's a batch optimization technique. And meanwhile, in 2009, we also have Leon Botou, who is advocating stochastic optimization for machine learning. You may have seen, for example, last Test of Time Award at NeurIPS, which was about this topic. And so that makes this risk minimization point of view relevant. So this formulation on the bottom, which I presented before, is exactly equivalent to the one on the top. It's just a matter of playing with notation. But now that we have this risk minimization point of view, you can start doing stochastic optimization. So what we did is that we listened to Leon, and we started experimenting with SGD, which in fact resembled the early approach by Olshausen and Field. But our first experience with SGD was in fact relatively mitigated for the following reason. In fact, we imagine that we start with alternate minimization, which is parameter free, and then suddenly we started using SGD, which is potentially much faster, but we had to tune the step size for every data set. And we really had a hard time to automatize this process of selecting the step size. So then we asked the question, well, can we exploit the specific structure of the problem and design an algorithm that would be in this setting as fast as a well-tuned SGD, but more practical? And in fact, so there were simply two ideas to do that. The first idea is simply a set of observations, which is that it turns out that if we knew in advance some optimal codes alpha I for every data point xi, then the dictionary learning problem will simply become the minimization of a quadratic function, which is represented here. And then the second observation is that this quadratic function is in fact parameterized by two matrices B and C, and these matrices are small. Their size is independent of n, which is the number of data points. Now the last observation here is that a quadratic function like this one, when the set of constraints satisfy also has some properties, then it can be minimized efficiently using block coordinate descent. And here that would give us some update rules for the dictionary that are very cheap, very efficient, and also block coordinate descent is parameter free, which is important for us. So then the second idea is that, of course, we don't know optimal codes alpha I in advance, which depend on some optimal dictionary. So what we are going to do is to simply try to estimate good matrices B and C, and we are going to do that in an online fashion. We are going at every iteration to draw a mini batch of data points, update the dictionary, and update these matrices B and C. And that uses, in fact, some ideas that appear in the literature of online EM, for example. Now, what about theory? So there was something nice about it. I mean, not only it will solve a problem in practice, but in theory, we could also prove some convergence guarantees to stationary points, which is a good property. And we could do that here by exploiting the structure of the problem, even though the problem was non-convex, stochastic, constraint, non-smooth, t-periodic something you do not like to analyze if you are doing stochastic optimization. So now we asked ourselves, well, what was the reason for the impact of this work? Well, it's certainly not because of the theoretical guarantees, but, well, the first reason is probably a matter of luck. We may call that a timely context in the sense that data sets were becoming larger and larger, and there was suddenly a need for more scalable matrix factorization methods. The other point is probably a combination of mathematics and engineering. So this work came also with an efficient software package, which was open source, called the SPAMS toolbox. And the reason it was used was maybe because it was maybe robust to hyperparameters. When you put software online, you know that most of the users are going to use it in a default setting. And in that case, it seems that it should work in practice in many cases. So the last point was some flexibility in the constraint and penalty design for the problem, which could allow to use the method in various contexts. So I should say that maybe this method was used in 90% of the cases for natural image patches, but from time to time we also received email of people who would use it in a context which had nothing to do with the original design, and it was pretty rewarding. I will give you simply 3 examples of papers that are using the toolbox. There is the first one published at PNAS that uses it to model tree leaves. We have also this recent paper that is using it to model spatial relations between genes in gene networks, and an alternate title about this work is called Mapping a Cell's Destiny. If you want to know more about it, you can Google that. It's a pretty interesting paper. We have also this nice paper which is using dictionary learning to remove confounding factors in gene expression data. And again, it's something which has nothing to do with the original setting. Now I would like to conclude my presentations with 2 things. The first one is that, well, these dictionary learning techniques or sparse coding are not completely disconnected from the hype of today, and there are in fact strong connection with neural networks. For example, if you have a data point X and a dictionary D, if you simply want to obtain a sparse code beta, a simple way to achieve this is to compute ReLU of D transpose X minus lambda, where lambda is a hyperparameter. And you see that when lambda becomes larger, beta becomes sparser. When lambda is very large, beta is equal to 0. So of course, if you do that, it's very cheap and you don't have any approximation guarantee. You don't have any guarantee that you would have X that should be close to D times beta, unless what you do when you are doing sparse coding by computing alpha here. But still, it makes it not that surprising that for dictionary learning, in fact, you can do end-to-end feature learning. It's something we have been advocated for a long time. Basically, you can do backpropagation, to summarize. You can also design convolutional and multi-layer models, as done by Zeiler and Fergus, for example. Turns out that at least first-order methods for sparse approximation, basically sparse decomposition algorithms, perform operations that resemble what neural networks are doing. And this link was exploited in the LISTA approach, for example. So that's a very strong link between dictionary learning and neural networks. And finally, my true conclusion. So I want to conclude with these nice pictures of Dorothy Wrinch and Harold Jeffreys, and simply ask a question, which is, their simplicity principle they have introduced in the 20s, is it a principle which is still relevant? So we would argue that yes, that simplicity is a key to interpretability and to model and hypothesis selection, especially when you don't have data that will allow you to choose between different models. It's very likely that simplicity, the next time it will have a huge impact, will be different than this L1 norm. Which form it will take, I don't know. And finally, I want to say that simplicity is also probably not enough. We kind of realize today that there are various forms of robustness and stability that are also needed. So that will conclude my presentation, and I will be happy to answer any question.
If you have any questions, please go line up at one of the microphones. Questions? Okay, let's.
So I noticed that you released software with this, which is extremely relevant with this conference because we've been trying to encourage submission of open source software with accepted papers. I was wondering what your opinions were on how much the success you had with this paper was due to having the software available.
So it's a good question. So the question is actually related to the new policy of ICML and Europe about software release, which is encouraged with publications. And the question is if the success of this paper was also related to the fact that software was available. I'm pretty sure the answer is yes. That was one of the points I raised about the fact that, yes, the impact of a work increased by a lot if you have software which is available, but you also need to make quite a lot of engineering effort to make it easy to use. Just releasing software does not necessarily increase the impact. So that's something I was willing to do when I was doing my PhD. Nowadays that I have many PhD students, I will not be able to do the engineering effort myself. But yes, I mean, I personally believe it's a very good thing to release software. It helps to have an impact also in other fields.
If any more questions? Doesn't look like it. Okay, so then let's thank and congratulate the speaker, and now we can go for coffee.
When life is pushing down, been used to hitting ground, I can be your safe and sound.